Fundamental theorem of algebra. Every polynomial with the degree n greater than or equal to 0 and a sub n is not 0 with complex coefficient have at least one complex 0. Okay. Complete factorization theorem. If p of x is a polynomial of degree n greater than 1, then there exists a complex number a, c1, c2, c sub n, so that a is not 0, so that we can factor this into each of the factor x minus c1, x minus c2, so on and so forth. Every polynomial of degree greater than 1 have exactly n0, provided that a zeroth multiplicity k is counted k times. So for example, if you remember a quadratic equation, it have two solutions, right? And for one that have only one solution, then there is multiplicity of 2. And the one that have no real solution, then it have two complex solutions. Right. So factor the polynomial completely and find all of it 0. State the multiplicity of each 0. Okay. So let's start with factoring. So recall that, like we said in the meeting on Thursday, if you have a cubed minus b cubed, this is the same as saying a minus b times a squared plus ab plus b squared. I then can rewrite x to the 6 minus 1. So x to the 6 minus 1 is the same as saying x squared to the third minus 1 to the third. I can factor this as x squared minus 1 times x to the 4 plus x plus 1. X squared minus 1 is the difference of 2 squared, so that x minus 1 times x plus 1 times x to the 4 plus x plus 1. I want to find all of it 0, so p of x equal to 0. This means x minus 1 equal to 0 would lead to x equal 1. X plus 1 equal 0 would lead to x equal negative 1. For x to the 4th minus x squared plus x squared plus 1 equal to 0, I can go ahead and do a u substitution. Let u equal to x squared. Then the equation becomes u squared plus u plus 1 equal to 0. I can solve this using the quadratic formula. U times negative 1 plus or minus square root of 1 squared minus 4 times 1 times 1 divided by 2 times 1. This is negative 1 plus or minus square root of negative 3 divided by 2. It is the same as saying negative 1 plus or minus I square root 3 over 2. So then it's telling me that u equal to negative 1 plus I square root 3 over 2, and u equal to negative 1 minus I times square root 3 over 2, but u equal to x squared. This meant that I can rewrite that x squared equal minus negative 1 plus or minus I times square root 3 divided by 2. This means x is equal to plus or minus square root of negative 1 plus minus I times square root 3 over 2. X squared equal negative 1. Okay. So right here, as you can see that we have 4 solutions here. So 4 solutions. Okay. And here you get 1 more. So in total we have 6 solutions. So there's 6 zeros of this polynomial. So in total we have 6 zeros. We have 4 complex and 2 real. Take a look at the next one. So p to the x equal to x to the 5th plus 6x to the 3rd plus 9x. So I expected to have 5 solutions here, counting multiplicity. So first of all, let's go ahead and factor x. So x to the 4 plus 6x squared plus 9. Okay. So p of x equal to 0. This means when x is equal to 0 and when x to the 4 plus 6x squared plus 9 equal to 0, this is the perfect square. So this is x squared plus 3 squared equal to 0. Okay. So x squared plus 3 squared is x squared plus 3 times x squared plus 3. That equal to 0. So then x squared plus 3 equal to 0 would lead into x squared equal to plus or minus equal to root 3, equal to 3. X equal plus or minus root 3. And since this is only one of the factor, and you have 2 solutions here. So in the other factor, you will produce 2 more. So in total, here we have root 3 with multiplicity of 2, negative root 3 with multiplicity of 2, and here we get an x equal to 0 with multiplicity of 1. So let's talk about finding a polynomial with a given condition. So we want to find a polynomial have degree 3 and 0 is a 3, 2i and negative 2i. So again, then p of x equal to x minus 3 times x minus 2i and times x plus 2i. So let's multiply this out. We get x minus 3. So recall I squared is equal to negative 1. Square root of negative 1 is equal I. We FOIL this. So we get x squared plus 2i minus 2i minus 2i squared. So that is x minus 3 times x squared minus 4 times I squared. So minus 4 times negative 1. So p of x is equal to x minus 3 times x squared plus 4. And multiply this out a little more. So x to the 3rd plus 4x minus 3x squared minus 12 is the polynomial that satisfies the given condition. If the polynomial have a real 0 and its complex number z is also a 0 to p, then its complex conjugate z bar is also a 0 to p. So z is of the form a plus bi. Then z bar is of the form a minus bi, is also a 0 of p of x. We want to find a polynomial degree 3 that have integer coefficient 0 at 1/2 and 3 minus I. So this means this is Z. So then we also have another solution at 3 plus I. Okay. So the polynomial that we're looking at is x times negative a half times x minus negative 3 minus 3i 3 minus I times x plus this is times x minus 3 plus I. Okay, so let's do some multiplication. So the first one is x times minus 1/2. The next one is x squared minus x times 3 plus I minus x times 3 minus I plus 3 minus I times 3 plus I. So x minus a half times x squared minus 3x minus xi minus 3x plus xi plus 9 minus I squared. So let's simplify this. Negative xi with positive xi, that's gone. Negative I squared, that is positive 1. So this makes 9. So this makes 10 here. So then p of x now become x times x minus a half times x squared minus 6x plus 10. Go ahead and multiply this out. X to the third minus 6x squared plus 10x minus 1/2 x squared plus 3x plus 5. And by like term, x squared minus, so negative 6x squared with negative 1/2 squared, that together become (11/2x squared plus 13x plus 5. Now we wanted to have integer coefficient, but here we have a 11/12, and this is a rational number. It's a rational coefficient. So in order to get integer coefficient, we multiply the entire polynomial by 2. So this is 2x squared, 2x to the third minus 11x squared plus 26x plus 10. Talk about the linear and quadratic factor. Linear and quadratic factor theorem. Every polynomial with real coefficient can be factored into a product of linear and irreducible quadratic factor with real coefficient. So for example, when you look at x to the third, in this case, this portion here is the irreducible quadratic equation with complex solution, right? When you factor it, you get a irreducible factor. Okay. So p equals x to the fifth minus 16x. Factor p into linear and irreducible quadratic factor with real coefficient. Okay, so p of x equal, I factor out x to get x to the fourth minus 16, and that is x times x squared minus 4 times x squared plus 4, and this is x times x minus 2 times x plus 2, times x squared plus 4. So note that here, this portion is the linear. Here, this x squared minus 4 is an irreducible factor, irreducible quadratic factor with real coefficient. And what if we want to factor this completely? We go one step further. So x squared plus 4 is really just saying this is x squared minus negative 4, right? And so I can write this as x squared minus 2i. I can write this as x minus 2i times x plus 2i. Okay, so then the polynomial with a complex factor is then become x times x minus 2 times x plus 2 times x minus 2i and times x plus 2i.